This session is going to be about talking a little bit about some different perspectives on what Neo4j does. You can look at today's session really as being a way of getting lots of different perspectives on things from different people. And in this session, I hope to give you a couple perspectives of my own on how I've come to see this technology, and hopefully you can come away with some of that and use that to add to your opinions and your growing perspective. Great. So a few takeaways of this session. I'm hoping you can come away with a better understanding of what the technology does to help you choose the right technology for the right job. You've got a plethora of technologies to choose from to do all kinds of different things. And my perspective on technology is each technology is built to solve a given problem at a given period of time, solve an important problem subject to technology constraints of the day. And we'll build on that as we go on. So if you understand the technology constraints Neo4j was designed for and the problem it's designed to solve, then that can help you apply it better. And then oftentimes the business is asking IT to solve problems that are intractable using technologies that you might already have in-house. And so how do you use what you've learned here to expand your tool set so that you can start to solve some of these problems that previously might have been considered unsolvable? And then finally, by understanding what's possible, not just how the technology works, but some of the examples, like as Jeff and others have given throughout the day, and as you're discovering, speaking to each other, of things that are done in maybe one industry or one use case can maybe apply to what you're doing. So we're going to talk about a few different perspectives, and again, to use the metaphor many of you may have seen of each session kind of is like a blind man touching a different part of an elephant. So it might start out like seeming like a pillar, or like a brush, like the tail, or like a snake, the trunk, and you come out with an idea of, okay, this is the elephant. This is what Neo4j is about. And the first perspective I want to give you is historical. And let's go back to 1979. Can anyone guess why I chose this date? This is when a company called RSI, which you now know as Oracle, came out with the first production version of a GA version of the first relational database. And at the time, the huge business problem that information technology could help address was business process automation, and especially the part of business process automation that involved all these mountains of paper forms. And this is the reason why in Database 101 classes, you still learn about the order form and how I break apart the order form so I can bring it back together and avoid redundancy and normalize and so on. The constraints of the day, where you had minimal amounts of RAM, that's a Commodore 64 chip, so that's actually a few years after 1979. That was probably big at the time. And then spinning platters, which were optimized for certain kinds of read and write patterns, namely sequential access. So relational databases came about and ended up, unsurprisingly, being really good at taking data and breaking down paper forms and storing those. It's data that tends to be predictable, that's structured in a particular way, where you have access patterns that tend to be more sequential. Fast forward to where we are today. Some of the most valuable problems today aren't that. That's 40 years ago. It's taking these dynamic real-world systems that are difficult to predict, that are hard to put in a box, that are hard to model ahead of time because I don't have a full grasp of the system or it's changing very fast, and making something of that. And then from a technology constraint perspective, that box is completely blown up. So you have vast amounts of RAM, you have machines with double-digit terabytes of RAM, and then you have ones that are economically feasible at half a terabyte plus. And then you also have Flash, which is much better able to do random I/O, which means which is really helpful if I've got these dynamic systems and I don't know what's connected to what and what's going where. You can't really pre-optimize ahead of time how you're going to store things in a sequential layout. You could for one query, but then your next query, it's going to start hopping randomly. And Neo4j was actually built from the bottom up to solve the kind of problem on the top left, subject to the assumed constraints at the bottom left. I joined 7 years ago yesterday. And at the time, actually, not everybody was using Flash, and not everybody had quite as abundant RAM. And this was a little bit less of a no-brainer. But now the hardware has evolved enough to grow into our vision of the world that we constructed the software for. That's one perspective. Let's shift and look from an IT portfolio perspective. You can really simplify and say that traditional databases are built for store and retrieve. So relational databases originally, in my paper forms example, I store the form, or I store a customer, I retrieve, store, retrieve, store, retrieve. And the other NoSQL databases aren't too different. I want to store and retrieve key value data at scale. I want to store and retrieve documents. I want to store and retrieve column families. And what you see at the bottom in this little circle is what are the number of hops that these technologies can accommodate. Since they're not really built for hopping across things randomly, usually you can get up to about 3, depends on the density of your graph. If you're less dense, like a human ancestry genealogy graph, you have each person has, on average, not too many kids and exactly 2 parents, 2 genetic parents, maybe more parents, but that's about it. There you can maybe get up to 4 or 5 hops, but not much more than that. Most social networks might have hundreds of connections, and then mileage varies by different kind of scenario. Then if you look at, let's call it big data technology, but most big data technology that your Hadoops and your enterprise data warehouses and so on tend to do 2 things. They aggregate and they filter. You can give it a number of dimensions by which to aggregate, and it'll aggregate, or it'll find needle in haystacks. You can run through millions, billions of records and do pattern matching. And then you've got this. So this is a way to look at the IT portfolio. And there's a cartoon I came up against a few years ago where if you actually try to apply that to what it is we're doing here today, is if you map on one end and say you've got data that's more discrete, it's less about the connections, it's more about the individual data points, and then at the far right side you have your connected data, then you can kind of map out a journey of, let's say, a maturity model, where at the far left you have data, you're just doing store and retrieve. And so we talked about what kind of technology is really good at that. And then for those of you who were around 10 years ago, just eyeballing the room, it looks like most of you were around with me 10 years ago, 15 years ago, when everybody was talking about turning data into information. Do you remember this? Turning data into information gives you sort of like your color coding around the data and what's the data. And that's where you have enterprise data warehousing and everything in Hadoop land and column optimized relational database access. So that's a step in maturity of understanding of your data. And everything else involves connections. Knowledge is being able to understand how things are connected. Insight is using the knowledge of how things are connected to find things that are interesting that I never would have known are interesting unless I had this knowledge. And then wisdom is understanding actually how I got to that insight. And that one's actually particularly important from an AI machine learning perspective, because AI explainability is something that's important not only for you, but for regulators and for people, for consumers ultimately who want to know why a particular decision was made, why was my mortgage denied, why did a particular recommendation occur. So that was a second perspective, and then let's do a third, looking a bit down at a more detailed level at the technology of what are the things about this technology that are different. If I had to pick one core thing that's different, it's this. And there's a fancy term for it, but called index-free adjacency. But what it actually means is that when you write the data, because in the graph model, you have individual data written as nodes, and then you have relationships that connect them, that as the storage engine actually writes that down to disk, you connect the data as it's stored. So every single node has a pointer that has like an address that points to a pointer that's either in memory or on disk to an adjacent relationship, which knows what node is connected at the other end, and this is bidirectional. And so I can find the node at the other end just by chasing a pointer. And what that means from a performance perspective is pointer chasing is one of the most simple, efficient operations that a CPU can undertake. And you can do a couple million of those per second per compute core, which is kind of like doing a couple million join operations per second per core. And not only is this very fast, but it's very efficient. So some of the stories you may have heard about a massive cluster of a massive Cassandra cluster, or Mongo cluster, or Exadata cluster, where you take highly graphy workload and it takes a massive amount of hardware, and then you put that on Neo4j. Not only do things get much faster, but you might need 1/10 the hardware or less. I see this quite a lot. And this actually, to me, is kind of remarkable because in my experience with technology, especially enterprise IT, you usually have to choose between things that are going to cost you a lot. Total cost of ownership is high, but then you have an incredibly high business value. Or between things where the business value is relatively low, like it might be the same business value, but then you have a high degree of cost savings. And here you kind of get both, which is pretty remarkable. And if you look at this, the impact to query response time, a good mental model for you to walk away with is, as the connectedness of a data set, I use the term density of the graph. So as data gets more connected, and then as your size of the data set grows, then as your, I don't know what happened to that on the right. That's weird. That should say Neo4j. As you move to the right and you have more and more connectedness and so on, and then you have more and more hops, then your response time goes it's either flat with Neo4j for the same query, or as you add hops, it tends to get to grow a lot more slowly, to be closer to linear. Whereas with other technologies, you're chasing through B trees with each hop for each piece of data. And B trees, the more data you add, they get deeper and wider. So basically these index operations can incur lots and lots of inefficient processing. So it's kind of not the best use of hardware compared to the pointer chasing approach. But also the queries can take very, very long. And in my first few months with the company a number of years ago, I went out and I spoke to all our customers because we didn't have that many at the time compared to now. And I heard the term so many times that we had queries that took minutes to run, or hours, or they would never finish, that run in milliseconds now. We started using the term minutes to milliseconds just to echo back this aspect. And another often overlooked piece, and one can get very technical about ACID semantics and what that means inside of an instance and across a cluster and CAP theorem and so on. But if you look at graphs, they're unique compared to, let's say, data that's stored in other NoSQL databases, in that little thing that I just animated, that little subgraph, that data all goes together. And it might be as simple as one relationship, and I know this relationship connects two different nodes, and I know that those three things go together. The relationship without either node doesn't make sense. You don't want a relationship that doesn't point to anything. What that means from a technology perspective is your technology needs to guarantee that these things will either all succeed together or all fail together, and then you need all the right, rollback and failure mechanisms. And we have a term for that, and that's ACID. And so we've been contrarian since the early NoSQL days in saying that if you care about the connections in data, you must provide these guarantees if you're going to have any sort of transactional updates. And then not only that, that's inside of a single machine. If you have a cluster for high availability reasons or for read scaling, then you need to make sure that the data propagates across the cluster in the same all or nothing fashion. And what you find is if you take another approach, let's say I'm going to take a database that is non-ACID, and there are, if I take Redis or MongoDB, which is starting to get a bit more ACID, or Cassandra, and I try to build a graph there, then you may end up with cases where the pieces of that graph get written in a different order, and maybe some will succeed, maybe others will fail. If everything succeeds, then you might have an intervening read transaction, which might try to chase to the end of a relationship where the node hasn't written yet and it looks like it doesn't end anywhere. So you can end up with some bizarre treatment of data that over time can lead to data corruption, which is not a good thing. Our chief scientist actually worked with some researchers at the University of Manchester who mathematically proved that corruption, that eventually consistent backends corrupt graphs over time as a function of what your write throughput is, basically. So this isn't good enough. We've never believed on the right side, so we don't want to do that. But it's a good, it's an interesting era where many of the assumptions that we carry around from having worked with relational databases for the last 40 years need to be questioned. And so these are some of the basic things that are worth questioning. And then Jeff and others have talked about the Cypher query language. So another aspect that's different is if you create a solution from the bottom up to support connected data via sort of a network or graph model, then you end up with this entire stack where things are different. And index-free adjacency is this thing that exists at the storage and then the memory layer. And if you float all the way up to the way users interact with the database, you end up with a vastly different query language based on ASCII-based representations of patterns, which can lead to much more efficient queries. And so this means less time writing queries, which means more time asking questions, and then it runs faster, so you get your answers faster, and so on. And I always like to think that if I'm the one who has to inherit a query 6 months after it's been written, which might be my own query, then I'd much rather inherit the thing on the right than the thing on the left. So zooming out, we talked about two of the foundational components, index-free adjacency, ACID, talked about the query language. There are a number of others. I won't go through them all in detail, but I guess a concept to keep in mind when doing technology selection and when also bearing in mind what kinds of problems can this solve is it's really designed from the bottom all the way up to the query language, to the language driver that uses the query language, to the tooling, and then back down to the clustering layer and the interactions between the driver and clustering to deal with connected data. We have this clustering architecture that supports causal consistency. That's a fancy way for saying read your own writes. And you can and read your own writes is a more expensive kind of operation, and you can choose, do I want my cheaper operation where two writes that might happen from my client application are tied together logically versus not tied together logically, and that affects what parts of the cluster your drivers will actually route your reads and your writes to. Lots of tooling, language drivers, and so on. There's a graph engine that does all sorts of cool stuff. And I guess Graph Engine is a simplification for everything from your statistics that are kept in the graph as the graph is updated to support your cost-based optimizer, to support the various runtimes that exist, and so on. And then kind of from first principles, Neo4j is optimized for today's hardware, but we like to work with vendors such as Intel and IBM on future hardware so that as the new hardware comes out, we're a step ahead for you. And then there's all sorts of enterprise infrastructure stuff that's maybe important as you get more towards production of all the various security things that you need, ranging from LDAP to Kerberos to fine-grained access control. And we're actually working actively on the next version of Neo4j 4.0, where we're going to be doing quite a lot in areas like a lot more in fine-grained access control and multi-tenancy in other areas. Quite a lot. I could spend an hour talking about clustering and all the things available there. One of the many things is being able to have topology knowledge baked into the clustering architecture, so that you're able to optimize traffic across a wide area network. We've made improvements in recent versions to be able to roll through upgrades of minor feature releases such as 3.4 to 3.5 without any downtime. We're continuing to add some constraints. So graphs are interesting in that you don't need to define schema ahead of time. Of course, once you actually have an understanding of your data, your schema, your application, it can be nice to start locking things down. So there's some things like node keys and property existence constraints that let you do that. Auto cache reheating is a nice thing that we added in the very last release, where rolling upgrades is done by taking down and bringing back up individual databases inside of a cluster. And so you get continuous availability through the cluster. But then when you bring back a machine, it can be painful to have the cache reheat in just the right way. So now the database will keep track of what the cache state was, that when you come back up, it will retain that. Same with backup, same with cluster propagation of new members. So lots of stuff there. Let's take a step back. I'd like to talk about what we're building and what we're building towards. And the first thing to look at there is, inside of an organization, who uses graphs? And really there are three main consumers of connected data. You have applications, you have people who work with data, and then you have business users. And from an application perspective, graph transactions is what most people use Neo4j for today. And interestingly, there's often confusion about what does analytics mean? Well, in many cases, transactional graphs, you might say, are analytic in the sense that the kinds of recommendations being done, the kinds of fraud detection queries being done might have not been able to be done in real time in alternate technologies, and so you might have pre-computed them in the past, therefore you think of it as an analytic thing. So it's really real-time analytics is some of this. And I also think about this in terms of transactional graph queries fit into one of two categories. Either they're deterministic, meaning there's exactly one answer. So if I'm doing identity access management or customer 360, all of my queries have exactly one answer. And then the other is more, let's say, probabilistic, where it's recommendation, fraud detection. And this gets interesting, where you can formulate, there's a formulating the queries way of doing that and getting your queries to be better and better at expressing a complex pattern. Or there's the other way, which I believe Amy is talking about, where you have connected features that I feed into some machine learning algorithm, and so my deterministic queries become fed by, say, 20 very small cipher queries firing off and being fed as input as features into a machine learning algorithm, which gets you into data scientists, data analysts, doing work to build the algorithms and build the features that then can feed back into these more non-deterministic transactional graph applications. And then last but not least, there's business users, as we've discovered and many of our customers have discovered, can benefit quite a lot from seeing their data as a graph. So what we do to enable the connected enterprise and those three consumers of data is we build a graph platform. And at the core of that is the Neo4j database, which supports transactions, which now is starting to get fairly mature in terms of its ability to support graph analytics, which I'll add, though, is a new exciting area for us and for the industry. So I think this is going to evolve quite a lot over the next few years. And then you can see this virtuous spinning cycle of AI. I see this as being the transactional engine will throw off data, which you can then analyze, and then that results in better algorithms, which then improves the transactional applications, and it's a feedback loop. And then you've got tooling to build and administer the graph. You've got tooling to do analytics, which we don't have very much of now, and that's an emerging area. The Graph Algo library is primarily what that's about, and then there's a sort of a labs UI that we have that you can use to run some of these libraries. Again, very, very young and exciting, fast-growing space. And having APIs and language drivers, tooling to do discovery and visualization, and then data integration. For those of you who haven't seen it, one of the ways that the platform is embodied from a technology perspective for end users is through the Neo4j desktop platform. And what you see here is a snapshot where I've just pulled in a few graph apps where the, first and foremost, if you're developing and writing Cypher queries, you've got the Neo4j browser, which is a visual interface for interacting with the graph with queries. And then you've got Neo4j Bloom, which is the graph visualization tool, and then a variety of other labs projects. And you can also, there are also standard APIs you could use to create your own. So something Alessandro will talk about later when talking about Innovation Lab is how within a short period of just a few days, you might be able to do a prototype that you can show to the business as a graph app that sort of plugs into this framework. This is, the desktop includes Neo4j, it includes all the dependencies for running Neo4j and makes it easy to manage your databases, your plugins, and so on as a desktop user. So that's available free with registration from neo4j.com and includes all this stuff. One of the things you've seen a lot of today so far, which is worth coming away with, is how graphs give you a new way to look at your data. And I always think it's fantastic to work with people who have a deep business understanding or deep technical understanding of their domain and their data, and who will jump out of their chair when you actually show them their data in this way, as opposed to all the other ways that they've had. So this is meant to complement other kinds of visualization, but also to make it easier to understand the graph. It's a good way to actually explain to the business what it is you're doing if you're building a transactional application, but it can be really a really powerful way of enabling business end users. Jeff mentioned a term that I like, which is fraud has a shape, and I got that out of an early customer of ours who had one of these workflow-based applications that would where you had fraud analysts who would spend time looking at each particular instance of possible fraud and determining whether, is it fraud or is it not fraud? And it would take about 10 minutes to determine whether it's fraud or not. That was with a spreadsheet-based view of the data. And then as soon as you started giving them this view of the data, they started being able to quickly just rule in or out, is it fraud, is it not, based on the shape. So fraud had a shape. This is another exciting emerging area, and I'm going to talk about 4 different ways of doing graph visualization with Neo4j. And the left side basically involves smaller deployments where you want to be more, let's say, more intimate or engaged with your graph. Bloom is a data exploration and navigation tool. It's a graph exploration navigation tool that's oriented more towards smaller number of users who are not necessarily technical, but can be. And so it's meant to navigate your graph, exploration focused. And then at the far opposite end, you have more publishing oriented to lots and lots of, thousands of users or stuff you want to publish on the World Wide Web. And then in between, you have more sophisticated graph visualization solutions from partners such as are here today, Kineviz and Graphistry, as well as there are a variety of other vendors here that have specialized solutions, each bringing their own flavor of how to engage and interact with graphs for different kinds of use cases. And then you've got, kind of in the middle somewhere is BI tools who tend to not offer a graph-based view of the data, but offer the complementary, maybe mapped-based or chart-based view of the data that's also helpful. And this is an active area as well that we're working in. You've heard a lot about this, so I won't say more other than grab your book on the way out and grab the Neo4j desktop so you can start to try all this out. There's, of course, more online with the user guide and lots of stuff on GitHub where the implementation of the graph algos lives. And as Jeff mentioned, we've been working closely with Databricks and the Spark community as a contributor, adding Cypher querying into Spark. So, if you rewind to the earlier part of my presentation where I talked about the laws of physics underlying how do you store the data and what does that translate into the kinds of queries you can do, don't expect to be able to do like a transaction, use Spark for transactional graphs and lots of hops. Expect more to use Spark because that's going to be a never-ending query, and Spark isn't really meant as much for these kinds of queries to run transactionally. Think of it more as if I have a massive HDFS environment and I'm peering at it through the lens of Spark and in a tabular view, this is going to give you a graph-based lens through which to view it, through which you can marshal up data as a graph, and then examine it in memory, discover some basic interesting things, and then if you decided something you want to work on, then you can actually pull it into Neo4j, and then from there you can do your visualization, which actually depends on a transactional backend, and you can store the graph-based data, the subset data as a graph. So there's a really nice feedback loop and virtuous cycle here between data in the Spark environment and in Neo4j that we're looking forward to adding. And then last but not least, I talked about query language, and we opened up, we've been big believers from the beginning and supporters of growing the category and saying this is an incredibly valuable new way of looking at data that stands to become one of the primary ways that we work with data in the future, that there may just be a graph era ahead for the next 40 years in the same way that there's been a relational database that's carried on for the past 40 years and of course is by no means over. It's going to keep going for many decades to come. And so we've always believed that for end users to be able to have a rational, valuable space that's pleasant to work in, you want vendor independence with respect to the language. And so in 2015, we actually announced that our query language Cypher was something we were opening up. And if you go to opencypher.org, you'll actually see quite a few tooling providers and quite a few actually graph database technology providers have added Cypher support. And so this is something we feel really not only great about, but is super critical for the space, that if we end up in a place where every competing vendor has a different language, that's not good for you, and it's not good for the space. So we've been working very hard towards that. And then when this grows up, of course, it wants to become a capital S, like formal standard governed under a standards body. We joined ISO a couple of years ago and been working closely with all of the players, all the primarily relational database players, to create a sister language to SQL that would actually incorporate aspects of use the foundational data types and aspects of SQL, as we've actually striven to do in Cypher, except where necessary, and then to add the kinds of pattern matching things we've done in Cypher as a new language. So that's years down the road, and Cypher is going to reign. I expect the de facto language for many years to come. But our goal is for the thing on the right to be highly compatible with the thing on the left, and it's feeling like that's quite achievable. And there's a vote coming up next week, actually next Friday, where the ISO group is going to vote, have like the first step in a series of votes throughout the year to move towards having a second query language to the side of SQL as a standard query language under ISO. So I personally see this as not only a big deal for graphs, that this is something that needs to happen, but the fact that ISO may agree, hasn't happened yet, but seems to be on track to agree that graphs merit their own query language is also a big deal, because up until now, SQL has basically absorbed every other model, JSON, XML, that's all become part of SQL. But graphs are different enough and important enough that this is going to become a focus for ISO. And then from there, you've got ANSI and other national bodies that can point to ISO in the same way they did for GQL as they do for SQL, assuming it gets called GQL. All right, last but not least, I want to talk about the community as an important aspect of product and what it is that we do as a company. Shout out to our sponsors today. Please take time to meet with them. They're all doing amazing stuff. They're part of a much broader community of technology partners, of systems integrators partners, and then we're always adding on to this. So the community is continuing to grow, and you can see one of our bigger partnerships that we announced recently, Google Next, is we were shown, Emil actually showed up in a video on stage where Thomas Kurian presented his vision for GCP being able to have great relationships with open source technology infrastructure companies such as Neo4j and initially these 6 others to create an amazing technology backed by and optimized by both companies, by the producers of the open source technology and the producers of the platform. So we also have very tight relationships with Microsoft on the Azure front and with AWS on that front, as well as with Pivotal and many others. So couldn't be here without the ecosystem. And that's it. I was initially going to save a bit of time for questions, but I think I'll give 7 minutes back to the agenda since we started late. And if you have questions, feel free to grab me or feel free to tweet me. This is my Twitter handle, or reach out to me on LinkedIn or however you want. So thank you.